The IS-7 is the heaviest Soviet tank ever built. Today, the Armored Museum in Kubinka displays a surviving example that draws attention from visitors from many countries. The vehicle weighs about 68 tons. It carries 12 machine guns, a naval 130 mm gun, and armor up to roughly 350 mm thick. In other words, the engineers set out to build the biggest and most powerful tank the Soviet Union had ever seen. Its main gun could punch through the armor of German tanks of that era from around 2 kilometers away. And yet this machine never fought in combat. The story of the project shows how designers created something that was far ahead of its time, only for military leadership to later decide against full-scale production. In the spring of 1945, Soviet armored units were pushing toward Berlin. T-34s and heavy IS-2 tanks were breaking through German defenses, but the command was already thinking about what came next. On the battlefield, German Jagdtigers and King Tigers had appeared, and their armor wasn't always reliably penetrated by the guns on Soviet heavy tanks of the day. That created a clear demand for a fundamentally new vehicle, one that could guarantee an advantage in any large-scale conflicts that might come in the future. In June of that same year, in Leningrad at the Kirov Plant, a design group led by Nikolai Fyodorovich Shashmurin began work. He had previously worked on heavy tanks of the KV and IS families, but this assignment required a different scale entirely. The team needed to create a tank that could survive hits from any tank gun in service, while also being able to destroy enemy armored vehicles at extreme ranges. The project received the factory designation Object 260. Shashmurin understood that simply making the armor thicker wouldn't solve the problem. The tank would become too heavy and too sluggish, like the German Maus, which struggled to move under its own weight. So the designers chose a different approach and used steep, rational sloping angles for the armor plates. The front of the hull took on a distinctive shape that tank crews later nicknamed the pike nose. Engineers set the upper front plate at about 65 degrees from vertical, which dramatically increased the armor's effective thickness. When a shell hit that kind of surface, it tended not to bite in and penetrate. It would glance off, shedding a large portion of its kinetic energy. The designers ran the calculations and concluded that the new tank's frontal aspect could withstand a direct hit from the Jagdtiger's 128 mm round from a distance of more than 1 kilometer. The team achieved impressive protection against the Jagdtiger's gun, which specialists regarded as the most powerful anti-tank weapon of the Second World War. No mass-produced tank of the time offered anything close to that level of armor. And Shashmurin didn't stop at the front. He extended protection to the sides as well, giving the hull sides about 150 millimeters of steel and sloping them too. At the time, tank design simply hadn't seen solutions like that. For comparison, the German Tiger II had side armor around 80 millimeters thick, and the Soviet IS-2 had even less. This new vehicle was meant to survive attacks from virtually any direction. The designers paid special attention to the turret. Its front reached about 240 millimeters, and the gun mantlet was built up to roughly 350 millimeters of cast steel. With numbers like that, no contemporary anti-tank weapon could reliably defeat the tank from the front. In effect, the engineers created a moving bunker, something that could endure the fire of an entire battery of anti-tank guns. But that kind of protection inevitably drove the weight up. Early calculations showed the tank would come in at more than 60 tons, and that created serious problems for mobility and transportation. Most European bridges wouldn't be able to carry it, and rail platforms would have needed major upgrades. Still, the designers prioritized firepower and protection over logistical convenience, because they were working from a concept that favored a handful of well-protected machines instead of hundreds of vulnerable ones. By the fall of 1945, the project had taken on a clear shape. On the drafting boards of the Kirov Plant, the engineers finished the outline of this vehicle as one of the final examples of the Soviet heavy tank program. Long test programs and rounds of refinement still lay ahead, especially the fight to optimize the vehicle's weight. But even at that stage, the concept already looked unusual. Once the designers locked in the basic armor layout, they ran into the next hard problem. A machine weighing nearly 70 tons had to do more than just move across a battlefield. It had to maneuver with confidence, climb over obstacles, and reach speeds closer to much lighter medium tanks. To make that possible, the engineers developed a fundamentally new suspension and running gear, packing in a series of technical innovations. For the first time in this design school, they used tracks with rubber metal joints. Earlier vehicles relied on all-metal track links that were loud on the move and wore out quickly. The new design cut the noise significantly and extended the service life of the track. Each link connected to the next with a single pin secured by bolts, which made field repairs and the replacement of damaged links much simpler. On each side of the hull, engineers installed 7 large-diameter road wheels. The wheels used steel cord tires with internal cushioning, similar to what had been used on some German heavy tanks. That reduced vibration and extended the life of the wheel's outer surfaces, although it still left the familiar metallic friction noise during movement. Mechanics mounted each wheel on its own swing arm, linked to a torsion bar, and additional hydraulic shock absorbers helped keep the ride smooth even on rough, broken terrain. The design also included bump stops in the form of coil springs. They limited the swing arm's travel and prevented the wheels from slamming into the hull when the tank crossed major obstacles. The crew adjusted track tension with a hex head screw. Turning it one way or the other let them quickly tighten a sagging track right in field conditions. Researchers and military evaluators noted the system's overall simplicity and reliability. While the suspension showed a high level of engineering polish, the choices around auxiliary armament remain a point of debate among specialists. On the IS-7, the designers installed an unusually large number of machine guns, giving the tank the ability to lay down dense fire in multiple directions at once. For example, on each side of the hull near the front, they mounted one fixed RP-46 machine gun in 7.62 mm caliber. The driver operated these guns, and to aim them he had to turn the entire tank left or right. For vertical adjustment, he essentially used the gas and brake pedals, which made the whole process of firing far more awkward. Those maneuvers also created a physical jolt for everyone inside whenever the driver tried to walk a burst onto a distant target. Armored housings protected the guns, and special mechanisms fed ammunition from separate compartments to the weapons through chutes. Empty belts exited through upper openings, while spent cases were ejected through lower slots. The system worked autonomously and didn't require help from other crew members. The designers then expanded the setup from 4 forward-firing machine guns by adding 2 more RP-46s at the rear of the hull, pointed backward. That let the crew fire at enemy infantry, trying to get in behind the tank without having to swing the turret around. On the turret itself, the engineers also installed a pair of rear machine guns of the same caliber. They offset them to the sides to preserve space for ammunition boxes. The system automatically dropped spent cases into small metal containers. The crew had almost no real way to deliver aimed fire with the turret-mounted machine guns. The only workable method required the commander to rotate his cupola, look back, figure out the direction of fire by watching the tracers, and then order the gunner to turn the main turret. In practice, that setup was inefficient and tended to burn through ammunition fast. The armament package also included a KPVT anti-aircraft machine gun in 14.5 mm caliber, mounted high on a tall pedestal. Because the mount was so bulky, the commander couldn't fire it from inside. He had to climb out and stand on the rear deck, where he was exposed to enemy fire. That choice clashed with the very protection principles the designers had been so careful about when shaping the armor. Overall, the tank carried around 2,500 rounds of 7.62 mm ammunition, plus roughly 400 rounds for the heavy machine guns. Supplying and servicing that arsenal demanded serious logistical effort, while the practical value of most of those machine gun positions was never clearly proven. Later on, test crews noted that at least 5 of the guns could have been removed with no real loss, and that it would have improved the vehicle overall. Along the hull sides, engineers added folding panels where the crew stored various equipment. In the same spaces, they kept inflatable external fuel tanks made from rubberized fabric, which looked a lot like canvas bags. The idea came from earlier tanks that carried external fuel containers directly on the hull sides, but these soft tanks turned out to be more compact and far easier to store. The crew opened the panels by hand, and if heavy tools like jacks were strapped inside, closing the cover again could take 2 or 3 people. Building strong armor and a reliable suspension solved only half the problem. Next, the designers still had to tackle the central issue of every super heavy tank: finding an engine that could actually move all that mass and still give the vehicle real maneuverability on the battlefield. The German Maus, for example, weighed about 188 tons and could only manage around 20 kilometers per hour, while its power plant struggled with constant overheating. The Soviet designers wanted to avoid that kind of weakness. They chose the M50T engine, originally developed for torpedo boats. It was a 12-cylinder, water-cooled diesel that delivered an impressive output for the era, about 1,050 horsepower. No production tank engine of the time offered anything like that. For comparison, the T-34's engine produced roughly 500 horsepower, and the heavy IS-2's power plant delivered only about 520. But the engine's naval origin created real packaging challenges. It took up a large amount of space in the rear of the hull and demanded a powerful cooling system. Engineers arranged the radiators and fans to push as much airflow as possible through the engine compartment. On the top of the rear hull, they installed armored filler caps for coolant, engine oil, and transmission oil. Access to the power plant for maintenance and repairs was a major headache. Unlike most tanks of that era, the IS-7 didn't have the usual engine deck hatches. No small flip-up covers, not even the little round access ports you'd see on a T-34 or an IS-3. To reach the engine, mechanics had to remove large perimeter bolts around the rear panel and then use a crane to lift the entire upper rear section as a single piece. It was slow, it required specialized equipment, and it essentially ruled out serious repairs in field conditions. The designers understood those limits and planned to refine the layout if the tank ever moved toward series production. For the prototype, though, the designers kept the existing layout so they could focus on testing the core systems first, and the mobility trials produced strong numbers. Even with a combat weight of more than 68 tons, the vehicle could reach speeds up to about 60 kilometers per hour on a paved road. That's unusually fast for a machine in this class, and it put the tank right in the same territory as much lighter medium tanks. The transmission had its own quirks as well. Early examples used a 6-speed gearbox, but engineers later replaced it with an 8-speed unit. That upgrade gave the tank smoother acceleration and better flexibility across different terrain. The shift lever followed a clear pattern. The driver started in first gear and worked upward step by step. A separate lever controlled direction of travel, and it worked in an unconventional way. Pushing it forward engaged reverse, while pulling it back selected forward drive. When it came to the main gun, the designers understood that a breakthrough tank needed a weapon that could smash fortifications and enemy armor at maximum range. They chose the 130mm S-70, developed from naval artillery. The barrel was almost 7 meters long, giving the shell a muzzle velocity of about 900 meters per second. An armor-piercing round, weighing roughly 33 kilograms, could penetrate the frontal armor of tanks in service at the time from a distance of more than 2 kilometers. For comparison, the German 88mm anti-aircraft gun pushed its projectile at around 800 meters per second and showed lower armor penetration performance. High-explosive fragmentation rounds were also very effective. they could tear apart field positions, dugouts, and lightly armored vehicles. With the loading mechanism in use, the gun could fire about 5 rounds per minute, while switching to manual loading dropped that rate to about 1 round. Even the higher rate only held for the first shots already staged in the feeder. Once that ready supply was used up, the rate of fire fell sharply because the crew had to spend significant time reloading the mechanism with fresh ammunition. Beyond the main gun, the design also called for a coaxial heavy machine gun in 14.5 mm caliber, along with 2 SGMT machine guns in 7.62 mm. On the museum exhibit, the heavy machine gun looks almost like technicians removed it at some point, then hurriedly put it back in place for display. The installation lacks proper standard mounts, and the paired smaller caliber guns are missing entirely, even though the engineers left the mounting points for them. The main gun's ammunition load came to about 30 separate loading rounds. The crew stored the shells and the powder charges in their cases separately, in dedicated racks spread throughout the fighting compartment. That reduced the risk of a catastrophic detonation if an enemy round penetrated the armor, but it also made the loader's job much harder. They had to handle 2 heavy components instead of 1 fixed cartridge. Inside, the turret shows careful planning, but it also put the crew under serious physical demands. The fighting compartment held 4 men: the commander, the gunner, and 2 loaders. Each had a strictly defined position inside this steel maze. The commander's cupola sat on the right rear of the turret and gave him relatively comfortable working conditions. Nothing blocked his forward view, and the distance to the gunner's back left enough open space that the commander's knees weren't jammed into the man in front of him. He watched the battlefield through 3 square periscope prisms, arranged around the cupola's perimeter. The viewing slots were shorter than on most tanks of that era, so each one covered a narrower slice of the battlefield. But the commander's main tool was a rotating periscope. The designers placed it in the hatch cover, giving him a full 360-degree view around the tank. Right behind the commander's back sat an ammunition rack, which meant he couldn't really lean back and rest while the vehicle was on the move. Near his seat were boxes of 14.5 mm ammunition, and a bit farther away were the smaller caliber rounds. In the same area, engineers installed the control panel for the internal communications system, which the commander used to issue orders to the crew. The turret also didn't have a traditional turret basket. Instead, the designers provided a dedicated foot platform for the crew. At the same time, the museum vehicle doesn't have the protective guard that would keep crew members' legs from getting caught in the turret's rotation mechanism. It's possible technicians removed it for inspection, or the manufacturer intended to add it later if the tank went into series production. During rotation, the turret mechanism posed a real hazard because it could pull various objects into its moving parts. Usually it was small items, things like compasses or radio code notes. But in some cases, those moving components could snag the crew themselves. The loader's stations were positioned on both sides of the gun breech and were almost identical. On the museum example, the seats have been removed, but ammunition racks remain inside, taking up nearly all of the available space. From inside, you can clearly see the slope of the side armor plates, and the shell stowage sits directly above them. There wasn't much free room, so the loaders worked in conditions that felt more like a submarine than a tank. The key feature of the fighting compartment was the loading mechanism with its feeder. This semi-automatic system made the crew's job much easier during sustained firing. The mechanism held 7 shells in the upper section and 6 powder charge cases in the lower section at the same time. After a shot, the breech opened automatically. The spent case dropped out, struck a small metal chute below, and the chute kicked it off to the side. The loading cycle worked like this. A loader moved the next shell, it dropped onto the feeder tray, and it began traveling toward the breech. Then he repeated the same step with the powder charge case. As the 2 components approached the gun, the feeder tray lifted up parallel to the hull roof and brought the ammunition onto the loading line. But the feeder didn't ram the shell all the way home, so to finish the job the crew used an electric rammer. If the loading system failed, the tankers switched to manual loading. In that case, the loaders used a special T-shaped tool and physically pushed the shell and charge into the breech by hand. The breech block then rose and sealed the chamber, and the gun was ready to fire. The crew repeated that sequence until they had used up all 6 rounds in the mechanism, plus the one the loaders had inserted at the very start. After that, they reloaded the feeder again. The layout of the ammunition racks made the loaders work even harder. Some of the shells were stored near the gunner's seat, and to reach them he had to lift himself slightly out of position. The designers left a special cutout in the backrest of his chair so a loader could reach those rounds without getting blocked. The process still wasn't comfortable. In real combat, the crew probably fired the ready rounds from the mechanism first, then topped it back up during lulls. The gunner's station sat to the left of the main gun and was tight on space. The manual aiming controls were positioned right in front of his chest, which left even less room for his legs. Even someone below average height would likely feel cramped. The designers placed the main sight so the gunner actually pressed his forehead against it while firing. That same sight also allowed him to engage targets with the coaxial machine guns. The fire control setup would look familiar to modern crews. Grips with triggers let the gunner control the entire aiming system. He adjusted elevation by tilting the grips forward or back, and traversed left or right by rotating the whole mechanism. That approach differed from the systems used on most Soviet and Western vehicles of the period, which often relied on a handwheel that felt more like a car steering wheel for horizontal aiming. To the gunner's left, engineers installed a manual turret traverse drive in case the electric motor failed. 2 viewing devices, similar to the commander's, gave the gunner a limited view. The preserved vehicle doesn't have a rotating periscope for all-around observation, even though the mounting point is there. Most likely the manufacturers intended to fit that device on production tanks. The driver's compartment occupied the front part of the hull. That's where the driver worked. The only crew member the design truly isolated from the rest of the team in the fighting compartment. He entered his position through an individual hatch in the front armor plate, which slid sideways along guide rails. The driver's station stands out for its space and its thoughtful layout. The seat mechanism could be adjusted in height to match the driver's build. At the same time, the standard cushion was fairly thin, so during long road marches the driver would still end up uncomfortable. Experienced crews typically use their own cushions to soften the pounding over rough ground. Aside from that, the ergonomics don't raise many complaints. The driver's vision system included 7 devices, 3 periscopes on the hull roof to either side of the hatch, 1 central unit in the hatch cover itself, and 3 prisms in the front. That amount of optics gave the driver excellent visibility, something that mattered a lot when maneuvering such a heavy vehicle in combat conditions. If needed, he could open the hatch and drive with his head out, but in real combat, that option would be completely off the table. To the left of the seat, the designers placed a stowage compartment for 7.6 2mm machine gun ammunition. Nearby, there was a shelf for the batteries. On the preserved example, the batteries themselves are missing, but the wiring for them is still in place. The instrument panel looks fairly standard for vehicles of that historical period and doesn't show any unusual engineering choices. The one truly uncommon detail is the speedometer, which the designers positioned on the far right. Earlier, that kind of placement had mostly been seen on tanks from the T-series. Engineers placed the main power switch directly between the driver's feet, which created some awkwardness in use. They put the starter button up in front of his knees. The horn also deserves a mention. On a military vehicle, it looks a bit out of place, but it served a practical purpose when moving in column or passing through populated areas. To the right of the seat, engineers installed compressed air cylinders that supported the engine's air start system. In brutal winters, when temperatures dropped below -30 degrees, a normal electric starter often couldn't crank a cold engine to life. That's when the driver opened a valve, compressed air rushed into the cylinders, and it spun the crankshaft until the engine finally caught. This dependable pneumatic system saved crews more than once in the harshest operating conditions. The driver controlled the tank with two levers that also acted as brakes. There was no separate brake pedal, and to hold the vehicle in place, the crew pressed locking buttons on the tops of the levers, turning them into a parking brake. For its time, it was an advanced system. It didn't allow the tank to pivot in place the way vehicles with side clutches could, but the IS-7 was still much easier to handle than earlier generations of heavy tanks. Nearby, the designers placed several fire extinguishers, a telescoping mechanism for opening the heavy hatch cover, and a hand throttle lever. In dedicated compartments, the crew kept spare bulbs for the instruments, individual first aid kits, and other small essentials for a march. Behind the seat sat ammunition boxes for the whole machine guns. By 1948, factories had built 6 IS-7 prototypes, and they went through the full cycle of factory and state trials. The vehicles posted strong results across the major categories: mobility, protection, and firepower. Successful testing could have opened the door to full-scale production, but the military leadership chose a different path. Alongside the IS-7, engineers were developing another heavy tank. At first, it was designated IS-8, and later the Army adopted it as the T-10. The new tank was worse than the IS-7 in almost every performance metric: thinner armor, a weaker gun, and lower speed. But the T-10 offered two advantages that mattered a lot: lower production cost and simpler operation. Building the IS-7 required specialized equipment, scarce materials, and highly skilled workers. Its 12-cylinder naval diesel cost as much as several standard tank engines combined. The loading mechanism was complex and prone to malfunctions, and crews could barely repair the tank in field conditions because the designers hadn't provided convenient access hatches to reach the engine. Moving a machine that weighed close to 70 tons created serious logistical headaches. Most rail flat cars and many infrastructure bridges simply couldn't handle that kind of load. The other model, the IS-8, weighed about 20 tons less and used proven components and assemblies. Crews could service and repair it much more easily, and transport units could move it without trouble using standard equipment. In a post-war economy, when the state was still recovering from massive destruction and rebuilding industry, cost became a deciding factor. Military leadership concluded it was far more practical to have 3 dependable tanks than one technically brilliant machine that was difficult to operate. In the end, industry produced only 6 vehicles from the first experimental series, along with a few more from a small pre-production batch. After the program was finally shut down, most prototypes were sent to be melted down, and others were used as targets on test ranges. Only one example survived. Today, visitors can see it on display at the Armored Museum in Kubinka, where it stands beside its German historical counterpart, the Super Heavy Mouse.